Hey, Charles.
Hey, Michael. How's it going?
How are you doing, Charles?
I'm doing great. Guess who stopped by the studio this morning?
Our TA from last year?
Yes, Pushkar stopped by, and he brought me ice cream, which I am eating.
Oh, good for you.
Just like old times.
All the times. Not just the old times.
So, yeah, that's fair. So what are we going to talk about today?
Well, actually, kind of in that same vein, this sort of idea that every time that we record, Pushkar seems to bring you ice cream is an example of generalization.
Oh, well done.
Thanks. I can make predictions about what might happen next time we record together based on generalizing from the past times that we've been together, even though it's kind of a different state. And so the idea of generalization is going to be to leverage learning in states where we've been to try to make predictions about states where we haven't been or haven't been very often.
Oh, that sounds interesting. So this will allow us to teach X's how to swim, for example, looking at your picture.
You don't like my pictures. The idea of the picture here is that we've got like actual data points, these 5 X's, but then we use this notion of generalization to kind of make predictions at places where we don't have data.
So it's machine learning.
Yes, actually. Very good point.
Cool. All right. Well, I look forward to it.
So this is the machine learning part or the generalization part of reinforcement learning.
Excellent.
So for us to be able to talk about generalization, it helps to think about states as actually being collections of features instead of just unanalyzed blobs.
So we're no longer going to refer to states as state 17 and state 19?
We can, but I think it's helpful actually to give them additional information like these features. So here's a concrete example to make this try to make some sense. Do you remember our taxi problem that we talked about before?
How could I forget?
In this particular environment, there was something like, 500 states, and in standard Q-learning type approaches, we would just think of all those different states as being completely different from one another. But we can also imagine tagging each of the states with some particular value, like whether or not, we didn't really have fuel when we talked about it, but whether we're low on fuel, what is the X coordinate of the taxi cab, this thing here? What's the Y coordinate of the taxi cab? Is the taxi cab currently near a wall, say to some direction, north, south, east, west? Each of these different features give us a little bit of a handle on the states and how they relate to each other, right? So if we have this state that we've got right here and we say move the passenger to some other position, we're still in a related state. The taxi hasn't moved, and it would be nice to be able to capture that. And so this notion of features gives us that idea. Does that make sense?
So that's a lot like how we talked about machine learning and supervised learning in our other machine learning class.
Exactly. Oh, yeah. In fact, we had words for these things. We talked about what were those words? It's the sort of the notion that different machine learning representations cause different things to be similar to each other.
Right. And there are lots of different ways that we could represent this state space other than whatever the different 500 states are. You have some of them up here, but we could have the coordinates of where the passenger is, not just the coordinates of where the taxi is. We could have things represented in sort of an egocentric way of what's the, Manhattan distance between a passenger and where the passenger wants to end up. There are all kinds of things that the ways we could describe things, and some of those things make some states look more similar than other representations would.
I think I remembered the term. I think it was inductive bias.
Inductive bias was something that referred to the way algorithms preferred one solution over another.
Oh.
But I think you're right, though, because different features sort of create different kind of inductive biases by making some states look more similar. So, for example, if we had this egocentric notion of how far away a person is from a taxi, then so long as a person is, say, 2 steps away from the taxi, any state where a person is 2 steps away from a taxi looks the same, or it looks very similar. In fact, if you look at this one you have now, she just drew that, right? The red circle is close to the orange square. If you were to move both the red circle and the orange square up, those 2 states would still be very similar because they're still 2 away from one another or have 2 in between them. But even though I don't move the red circle, if I take the orange square and move it to the right, then that's less similar because they're farther apart.
Okay, and though we're ignoring walls the way that you described that, right?
Right, I'm ignoring walls.
We move both of these up by 2. We're 2 apart, but it does feel kind of different because we don't have to go around the walls.
And if it's different or not different depends upon the state features that you use.
Okay, do we have a name for that, or is inductive bias an okay stand-in?
It's a representation, right? It's a representation issue. Some representations are better for some things than others, and you can learn differently depending upon what features you choose.
Okay.
For example, here's a great feature. For every state, here's the set of actions you should take to accomplish the goal. That's one representation. That makes learning really easy.
Ah, yes, good point. So let's talk about what we're actually going to learn.
Okay.
Now that I've given some kind of motivation for this notion of generalization, it might be worth talking about what exactly we are trying to generalize between different learning opportunities.
Okay.
So what are the functions that we're actually making use of when we're doing reinforcement learning?
What do you mean?
When we're learning, we're actually generally learning some mapping, right? So this is true in reinforcement learning in general. There's some mapping from input to output.
Oh, I see what you mean. So, well, the whole goal, of course, is to learn a policy, which is a mapping from states to action.
Great. Okay, that seems like a really good place to start. So policy maps states to actions.
But that's usually hard. So we usually learn some kind of intermediate thing like a value function.
Well, let's just stick with policy here for a
Okay.
second. So in terms of the policy, generalization would mean that to the extent that similar states have similar actions, then we could learn what the right action is for some states and then guess what the right action is for other states using some kind of, I don't know, function approximation, some kind of supervised learning.
Right. So if you're in a state where an anvil is about to hit you on the head, you should probably jump out of the way. That's probably true for every state where an anvil is about to hit you on the head, even if you've never seen the specific details of that state before.
Yeah, I mean, it could matter whether or not there also is a shark tank right in front of you. So when you jump out of the way of the anvil, you actually jump into the shark tank. But yeah, I think that's exactly right, that we want to be able to say across lots and lots and lots of related states, that we could be using the same kind of action.
Right.
But I think what you're pointing out is that we don't know how to learn the policy directly anyway when we're talking about these kinds of reinforcement learning algorithms. So we usually learn a kind of a stand-in for it.
And my favorite one is the value function, which is where you're now mapping states to some number, to R.
Right. So we can map, for example, states and actions to the estimated return. That's what the Q function does. And that's another function that we could be trying to learn. And this is another function where generalization might be an option, right? So to the extent that similar state action pairs have similar returns, again, because if an anvil is about to hit you on the head, probably that's a bad state. You're in a bad situation. Across all the different kinds of states where an anvil is about to hit you in the head.
There you go. That's you. You should draw a picture of me standing off to the side to your left. I have the world's tallest neck.
Yeah, so let's say I'm in a state where an anvil is about to hit me in the head. There's lots of other details that are sort of not that important in predicting what the estimated return is going to be.
Mm-hmm.
So you even look kind of concerned.
Oh, that's supposed to be me?
Yeah, you're tall.
Okay, fair enough.
So this is another place where we could be doing function approximation is in the actual Q function itself. And there's a third one that I think is actually really important and interesting, and that is the model. To the extent that you can actually do a good job of predicting next states, transitions for related states, then you could actually be doing function approximation or generalization in the model as well.
Right. In fact, that's probably very, very important often.
Yeah, it's not only is it important, but it's actually often a really natural place to do it because when you're learning a model, right? So what is it about learning a model? You're in some state, you take some action, and you observe what next state you're in. These are actually supervised examples of transitions. Mm-hmm. So unlike learning the policy or learning the value function, when you're trying to learn the model, you're actually getting standard supervised examples.
Nice.
So that being said, using function approximation in models, it has been done in the field, but it's not that well understood. In particular, you need models that can actually predict many, many steps ahead to be able to be used effectively for planning and decision making. Mostly what researchers have focused on is function approximation in the value function. So generalization in the value function. So that's what we're going to look at in the rest of this lesson.
Okay, cool. Look forward to it.
So I think it will help if we think through what the basic update rule is when you're doing reinforcement learning or Q learning, and then to try to adapt it to this notion that we're representing our value function using some kind of function approximator.
Okay.
So here's a way to think about this. We've got our Q function that we're going to try to represent as some function of a set of parameters or weights, maybe let's say one set of parameters for each action.
Sure.
And what f is doing is taking a state and translating it into a set of features. We're going to feed those features and the parameters of the function into something called f, and what will come out of that will be the Q value. So this is intended to be fairly general, and we'll talk about some specific examples of this in a moment. But so let's just imagine that Q is being represented by some kind of function approximator, and here's how Q learning works. We have an experience tuple that comes in, state, action, reward, next state, and then we do an update. Now, what's the update usually? It's we try to move the value of that state action pair a little bit towards the reward plus the discounted value of the next state S prime. So that's the Bellman equation, kind of hidden in here. And the difference between that and the current Q value is the TD error. And what do we want to do with the TD error? The TD error tells us, is our current prediction too high, too low, just right? Does it like porridge? And what we want to do is change. Oh, that's the three bears, I guess. But the fact of the matter is, we actually need to know the direction that we should be going. Are we too high or too low? And we want to move the parameters that represent the Q function. So a given weight, say W super A sub I, we want to move it a little bit. This is a learning rate alpha in the direction of that TD error. But how much do we move the weight? It depends on how that weight actually influences the Q function, right? So what's the partial derivative of the Q value for that state action pair as a function of that particular weight that we want to change? And we're going to change that weight proportionally. We're going to change things proportionally to that gradient. So this should look kind of familiar. Does this look familiar?
Yeah, it looks exactly like the, Woodruff-Hoff update rule, the things that we did with perceptrons. It's a normal kind of gradient update rule.
Yeah, right, exactly so. Right. And so when you're representing a function in terms of a set of parameters, we want to know, how do the parameters impact the value that we're predicting, and let's move those parameters in a direction that makes the prediction more accurate. So this is a way that we can actually view Q-learning as an update rule for underlying parameters of a function approximator.
Right. And I guess the only difference is that, unlike the sort of y star minus y thing that we used to do, this is what we got on this particular step. So that's what makes a TD error as opposed to, actual error. If that makes any sense? Does that make sense?
Yeah, I think that's exactly right. So when we're thinking about supervised learning, what's happening is we have some kind of output for our current input, and we'll call that y, and then we have a target output y star, and we want to change the parameters of the function so that instead of getting something like y, we get something much more like y star. So I think what your point is that this Bellman equation kind of value and this kind of current prediction do play the roles of y star and y. So this, I think, is a really good analogy. But one way that it's different is that y star, when we're doing supervised learning, is actually the right value, right? It's coming from some kind of trusted source, and it is the label. Here, we're bootstrapping, which I think is a kind of wrapping. And what we're doing with bootstrapping is we're using our current predictions as a kind of way of making a target for what our other predictions should be moving toward. So this should look a little bit unnerving, but it's not a bad idea, but it's also not clearly a great idea because instead of using real labeled data, we're actually making up our own labels using the current prediction from the Q function.
Right.
And we'll see, sometimes this can really run us into trouble, and we have to be a little bit careful to make sure that it doesn't.
Okay.
All right. So this is in a very general form. I think it would be helpful, though, to make it make more sense if we dive in and think about some particular representations of the Q function.
Okay.
The particular case I'd like us to talk about in more detail is linear value function approximation. So that is in particular the case where our Q function is represented as a weighted linear combination of the features that represent the state and maybe the state in action, but we're going to keep the actions separate for now.
Okay.
So this is how the Q function can be represented if we're doing things linearly. So we have this set of weights, WA sub I, and we have a set of features, or at least this function f that maps states to particular feature values. And let's say we've got n different features. So if we're representing things linearly, what we're doing is we're saying, let's sum over all the features for the current state, the value of that feature, times the weight that is being used to represent the Q function for this action. And just, sum them up. Essentially take the dot product between this feature vector and the weight vector. And it's these parameters, these W super A's, that are actually providing us the generalization, the ability to make a prediction to new states, because there's parameters that are shared between all the different states.
Sure, that makes sense. So it's like a neural network with nothing nonlinear going on.
Yeah, in this particular case, it is exactly a linear function.
Fair enough.
Which you can think of as being a neural net without any nonlinear and with a single layer.
Yeah, so in fact, you have a whole set of them. You have a whole set of neural networks all kind of happening in parallel. I suppose you could claim that they're that they're one neural network with a nonlinearity, which is kind of some kind of max function or something that figures out which action you should take based upon each of the QS of A's. And so you really are kind of learning a neural network.
Yeah, I can agree with that. I mean, we're gonna talk a little bit more about using more general neural network structures in this setting instead of just linear weights. But the linear weight case is kind of easier for us to think about. And there's actually been a tremendous amount of research on this particular case because the hope has been that it's more well behaved than what we get with nonlinear function approximation.
Usually is.
Let's think a little bit about what these weights are actually representing.
Okay.
One way you can think about the weight for a feature is that it gives a kind of sense of importance for each of the features in how much they're contributing to the action's value.
Sure. So if the weight sup A sub I is 0, then it doesn't matter what the feature is. It doesn't contribute at all.
That's right. So then it completely ignores the feature for that prediction.
And if the weight is a billion, then it means a lot, probably. And if it's negative a billion, it also means a lot, just in the different direction.
Right, sort of anti-importance.
Well, not necessarily. I mean, the feature depends upon how you want to interpret it. The f sub I produces a negative number, and you're actually, the weight is also negative. You're saying that that feature is really important.
Right.
And the negativeness just, it's kind of a function of the fact that you want Q values to be higher if you're going to use them.
Okay, all right. I think that's a good way to think about it. All right, so this kind of makes sense to you? Do you feel like you appreciate the notion of a linear value function approximator?
Yeah, I think so. Yeah, that makes sense. You just add up all your features and weight them appropriately.
Cool. All right, so let's kind of make sure that we understand this.
Okay.
So this is a good way to make sure that you're really on top of this. Let's do a quiz. So in particular, we're going to I put back on the slide two things from the past slides. One is here is a linear representation of the Q function. So Q of SA is represented by a weighted sum of the features for that state, and the weights depend on the action. And here is our weight update rule. This is in its very general form. The weight super A sub I is going to be updated according to the gradient of that weight with respect to the Q function. So let's make sure we get this, and let's actually compute that gradient. So this is actually not super helpful. This is probably what we want. How does the Q function for SA change as a function of some particular weight, say WA sub I? So I'm asking if you could do some, I'm going to say calculus.
Calculus.
Yeah.
Okay, sure, I can do that. You basically just want me to tell you what the derivative is in the case where you have a linear function.
Right, because that's going to tell us how we actually do our update. When we get a state action reward next state tuple, we're going to want to figure out how to bump up the weight. We're going to take the TD error times the learning rate times that derivative. So what is that derivative?
Okay, I think I got it. So go.
All right, what's your derivative?
Wait,
What?
Wait. I need to remind myself what the answer is. Let's see. So in this case, f of I is the constant and w is x. So it's just going to be f of I. C of x, the derivative of c of x is c.
I see. So you're saying since we're taking this weighted sum, how does any particular weight depend on it? Well, for the weights that we're not actually talking about right now, their corresponding coefficients don't have any impact on how things are going to change.
Right, they're all 0.
And for the weight that we are actually asking about, the derivative here is really just the constant in front of that weight. So let's see if I see what you're trying to say here is the Q function changes as a function of that weight is really just the feature with respect to the state that we're looking at, the ith feature.
Right.
Yeah, I think that's right. We're going to call that right.
Yeah, I was talking about c's and x's because I was just trying to remember how to take the derivative of a linear function. So y equals c times x. The derivative of y is just c. So I was just thinking out loud about which was c and which was x. And the x is the w. That's the thing that's going to change. And the c is the feature.
Right. And so it's helpful to kind of remind yourself that w are the variables in this case. Those are the things that we're looking at changing. And these fi's, even though they look like they could be variables, this is a constant. This is something that's just a fixed value given to us as a function of the state and which feature we're talking about.
Exactly.
Cool. All right. So very simple.
And I was right.
Yes.
Yeah. We should do more of those simple quizzes.
So that seems like a good idea, and I think it's worth asking whether or not it actually works.
Does it work?
Well, it's complicated.
Tell me more.
There have been some examples where things worked out extremely well. So let me just quickly summarize some of them so you have a sense. You mentioned neural networks. So neural networks, including with nonlinear connections, have been used with backpropagation in this context. Folks like Jerry Tesaro and Tom Dietrich have gotten some very nice results. creating learning systems that can actually do some fairly complicated things and some difficult tasks.
Like what?
Well, so Jerry Tesoro's work was in backgammon, and he actually used the same kind of approach in Jeopardy in the Watson system for figuring out how to do decision making. What's the right strategy for handling different situations in Jeopardy? And the value function was being predicted using a backprop net. In Wang and Dietrich's work, they were actually predicting the likelihood of success of various sort of shuttle scheduling strategies. So they were actually doing for NASA shuttle scheduling strategies.
Say that 3 times fast.
She sells seashells to the shuttling scheduling system.
Sure.
So those worked out really well. That being said, there's not that many other people who've gotten that to work effectively. I certainly, whenever I say to my students, look, these things work so well, why don't you try it? They don't seem to be nearly as successful as these folks have been.
Hey, I got it to work for my master's thesis.
Did you really? For what problem?
For tic-tac-toe, and then for a vision problem that after I went through all this trouble, I realized was just learning round.
Oh, that's impressive, in quotes.
It was impressive enough to give me a master's thesis, which I think was the important thing. So maybe the impressive thing is that I got a master's thesis out of it.
At MIT, of all places.
Of all places.
So it does sometimes work. I find that it's kind of difficult to get it to work consistently. What happens often when my students try this is they get a system that actually tends to start to learn well, and then it goes into some kind of a death spiral because, as I mentioned before, the bootstrapping aspect of this means that you're really dependent on making solid predictions based on your previous predictions. And when they start to go south, the whole thing can fall apart actually really quickly. That being said, there's some other function approximators that actually have been more successful that are variations of linear function approximators. So Rich Sutton in particular has gotten CMAC to work on a whole bunch of tough problems. CMACs are CMAC. It's a particular kind of function representation that is like a neural net, except for that first layer isn't really learned. It's kind of decided in advance how you're going to break up the input space. And so it really is kind of just a generalization of straight up linear. These can be really effective, but they don't generalize very aggressively. And that's part of what makes them a bit safer to use in this setting. Linear networks are, like we mentioned before, the learning rule is really simple for those, so that's great. People like Satinder Singh and Ron Parr have gotten cool things to happen for things like cell phone channel allocation, and so that's pretty cool. You have to be really, really careful about what features you use, right? Because actually, I probably should have mentioned this before. The important thing about the features, I'm going to say that it's important that we find features that are both computationally efficient and value informative. And what I mean by that is computationally efficient. What would be an example of a feature that would be really, really great, but is not particularly computationally efficient?
The one that tells us what the proper action is? I don't know.
Or what the value is actually in this
yeah,
case.
sure.
Yeah, exactly so. So if there was a feature that actually encoded the value function, that would be great. That would be really good for learning. The thing is, we don't know how to get that feature efficiently. If we did, we wouldn't have to learn at all.
Right.
So we have to somehow get features that we can extract efficiently from the state. But again, that's really easy to do. We can just return the state as a feature.
Mm-hmm.
It's really important that it actually also be value informative, right? So that one feature actually gives you lots of information about what the predicted value ought to be. So somehow balancing these two things is often very tricky to get to work.
Right. So going back to our taxi example, if it turns out that knowing how far away the taxi is from some place or how far away a passenger is from some place, and you can compute that pretty easily, then you should do it because it's helpful. And in your learning algorithm doesn't have to figure it out. And so that would be a good thing, right?
Yeah, so distance to passenger could be something that's both computationally efficient because you can just kind of pull it right out of the state representation, and probably value informative because it's actually very relevant to know, are we close to being able to pick up the passenger, or is the passenger quite distant and difficult to reach? So yeah, I think that's probably the kind of things that we would want. We probably should try that before we tell people that we think that's a great idea. But in general, these are the kind of properties that you're trying to balance.
Okay.
And I want to mention, because this is very hot right now, another example of using neural networks to learn value functions has been carried out recently by Google DeepMind, and they were using deep neural networks. Do you know what deep neural networks are?
Yeah, they're networks that are very profound.
Yes, they're poetic neural networks.
Mm-hmm.
No, they are neural networks that are neural networks, except some of them have, where instead of, say, 3 layers, they can have 10, 15. They can actually be quite substantially more sophisticated and complicated. And they often involve using things like convolutions. to work well on visual kinds of inputs. So what Min et al. Did at Google DeepMind is they actually learned effective strategies for Atari video games, mapping the screen, the pixels on the screen, to joystick actions, which is really neat.
It is.
Right? I mean, so it's actually learning to play the game given very similar kind of input to what people get. And in fact, they were able to get it to learn very effectively to the point where you could argue that it was comparable to people on average.
At least on some games. But did it learn how to play thermonuclear war?
No, it learned that the winning move is not to play.
Oh, nice.
No, that's not true. That was a War Games reference. And in fact, it did not learn not to play. It was not given the option to learn not to play. It just had to play whatever it was given.
Grad school.
And we're back. No, it is true that on some of the games it was superhuman, and in other of the games it was way, way subhuman. And that was why I said you could argue on average that it was about human level.
Okay, but that's like arguing that on average, if I have my head in an oven and my feet in ice water, on average, I'm comfortable.
Yes. We're not going to get a chance to talk about a lot of the details on this, though it's just a great example of reinforcement learning applied to a difficult problem and clever engineering tricks. The one thing that's worth noting is that in addition to using deep nets, which are kind of in vogue at the moment, they also did a couple other things in changing the way that training happened that I think were really, really important for getting the kinds of results that they got. And so it wasn't just a matter of, hey, let's just use deep nets. It was like deep nets plus really careful training so that you don't get these kinds of catastrophic death spirals. Like, again, what my students and I have tended to see when we try this stuff. So this kind of does it work successes story is not really the end of the story in the sense that, well, so we assigned some reading. I think these were reading associated with this current lesson. 3 papers, Tesaro, Boyan and Moore, and Sutton, which kind of tell an interesting story, which is, I think, a really nice summary of what the state of the art is here. So Jerry Tesaro got TD Gammon to work really well. So that's a 3-layer backprop net for learning to choose moves in backgammon. And it worked great. So everybody thought, hey, everything works great. So then Boyan and Moore wrote a paper where they showed that there's some very simple examples where things ought to work well, but they need not. They can actually work extremely poorly. Using this general approach of substituting in a function approximator for a Q function can lead to terrible results. So it need not work. Then Sutton had a reply to that where he published a paper that said, yeah, but you can do it if you do it right. So he actually replicated the same results that Boyan and Moore showed not working and showed that if you change the way that training happens, you could get those particular things to work. But this really is just, the argument is it need not work, but it need not work, which is not really a very strong kind of guarantee. It's not like it has to work or it has to not work. So this is kind of where we are now in terms of our understanding.
So what's the Pollock thing at the bottom?
Pollock. Oh, sorry. So yes, I just wanted to point out that why did backgammon work so well? It might not have just been the fact that it was reinforcement learning. It might have been, well, backgammon's kind of a good thing to learn this way. So Jordan Pollock had a paper where he showed that genetic algorithms can also do particularly well in backgammon in particular. So it might not have been that Jerry Tesaro discovered that TD is really great. He might have discovered that backgammon is really great as a test bed for TD.
Oh, yeah, I remember that. In fact, the argument that Jordan made was that because it's so random, it forces you to do all kinds of exploration and keeps you from falling into certain traps that made generalization powerful. And in fact, if we compare it to Isabel's master's thesis work on something that you thought was simpler, like tic-tac-toe, it actually doesn't do terribly well on tic-tac-toe, and that's because it's so deterministic. There's huge chunks of the state space you kind of never see, even when you're trying to do this generalization.
Yeah, okay, so I would summarize that by saying that nearby states in tic-tac-toe don't necessarily have nearby values, right? You just move one X to a different place on the grid, and the whole gameplay is very, very different. Backgammon, because it has such a tremendously influential random component, if you move one piece, it can change things, but it's not going to change things, night and day. It's going to change things gradually. And so that kind of gradualness means that function approximation is probably going to, well, it could at least work out well.
Maybe. It's certainly a good argument.
So what I'd like to do is actually step through a concrete counterexample that really does show that a particular way of doing this kind of training can fail in the worst case. And this is an example due to Lehman-Baird, and it's, devious and clever.
I like devious and clever.
So here's a really simple MDP. You ready? It's got 6 states and then a 7th absorbing state.
Okay.
For each state, there's exactly one action. There's no stochasticity. There's no rewards of any kind. They're all 0. So this is a really simple example, right?
Sure, that seems pretty straightforward.
All right, so then what is the optimal value function and policy for this example?
The optimal value function or the optimal policy?
I asked for both.
There is no optimal policy. It doesn't matter what you do. You just have to do the one thing.
There's only one policy, and it is optimal by definition of optimal.
And the value function, the proper value function would be 0 everywhere.
0's everywhere, right? Because there's no rewards anywhere. So this is super duper simple. And if we had to learn this using Q-learning or something like that, presumably this would actually learn quite quickly. What we're going to do, though, to make life difficult, is we're going to do this in a function approximation setting, linear function approximation, with this following set of features. So there's the 7 states in the picture, and associated with each state is a feature vector, and there's 8 features that are part of that. Feature 0, 1, 2, 3, 4, 5, 6, 7. Feature 0 is 1 for all these states and 7 for the repeating state. And interestingly, we have it set up so that these other features are actually completely indicative of which state you're in. So state 1 has feature 1 being true. State 2 has feature 2 being true. State 3 has feature 3 being true, or at least, and by true I mean 2, I guess.
2, yeah.
And so that's kind of the representation here. So state 6 looks like 1, and then 0's everywhere except for feature 6, which has a 2, and then a 0, right? So this feature representation is actually really close to being just a table.
Yeah.
So I'm going to say near tabular, in the sense that if we get rid of this first feature, there's going to be one weight that represents the value for state 1, and one weight that represents the value for state 2, and so forth, and one weight that represents the value for state 7. And so it's exactly just a table, one weight or one table entry per state.
Right.
And all we've done is kind of made it a little bit, more by having this extra feature that we ought to be able to just ignore, right?
Mm-hmm.
And we should be able to represent things pretty well. So in fact, I think it's worth asking, can we represent the optimal value function using this set of weights, right? So if our parameters are W0 through W7, is there a way to set them so that the value function that we get is the actual value function for this MDP?
Sure, there's one easy one.
And what's that?
Set them all to 0.
Right. So we're taking this weight vector of W's and taking the dot product with the feature weights. If the weights are all 0, it's always going to predict 0, which is actually the correct answer for this MDP. So it's really easy to set the weights so that happens. Is that the only way to set the weights to make this happen?
No, because in fact, for each one of those states, there's only 2 features that are turned on, and there are different 2 features for every state except for state 0. So you could be pretty clever about it. So I think if you make the weight for 0 -1, maybe, and then make features 1 through 6 1/2, that would get you 0 for everything except state 7, and then state 7 just needs it to be 7.
7 or a 7th?
7.
7, good. So in particular, this weight vector times this feature vector is going to give us, -7 plus 0 plus 0 plus 0 plus 0 plus 7, so 0.
Mm-hmm.
For this other one, it's going to give us -1 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 1, which is 0. So this is a weight vector. So not only can we represent the value function, but we can represent it in multiple different ways. It is multiply representable, which I spelled wrong. Multiply, which is spelled the same as multiply, but it's representable in at least 2 ways.
Actually, an infinite number of ways, because you could take that vector, -1, 1/2, 1/2, 1/2, whatever, 7, and multiply it by any constant, including 0, and it'll work.
Oh, nice. Multiply it by 0, you get that first weight vector that we talked about. Anything else that we get, we're multiplying 0 times a constant. So in fact, there's an infinite set of weight vectors that all capture the optimal value function, which is all 0s. And so, we have plenty of rope. We should be able to build a rope ladder.
Yeah, hang ourselves.
Oh, ultimately, that's actually what's going to happen in this case.
Mm-hmm.
But, it seems quite friendly, right? It's also tiny, right?
Yeah.
These are all things that seem like it should make it so that it's really easy to get this right.
So then let's get it right.
Yeah, well, so it turns out that what Baird showed is that if you give it the right sequence of updates, it will actually spiral out of control. So let's take a look at that.
Okay.
Here is a bad sequence of updates for this particular example. So I rewrote the value function for all the different states, all 7 states. They're all, remember, dot products of the weights with the feature vectors. So V1 can be written as W0 plus 2W1. V2 can be written as W0 plus 2W2, and so on. State 7 is the weird one, right, that has 7 times W0 plus weight 7. And we have to change the W values so that we actually are representing the value function correctly. So let's consider the case where we start off. We're just going to get this process going with the weights positive and the value of state 7 much bigger than the others. And we're going to update things round robin. We're going to say after a transition from state 1 to state 7, using the only action that we've got and getting no reward, because there's no reward. We update when we go from state 2 to state 7, state 3 to state 7, state 4 to state 7, state 5 to state 7, state 6 to state 7, and 7 back to itself. So these are all the possible transitions in this MDP. So we'll just update all of them one at a time, and then do it again, repeat. And just for concreteness, let's say that the discount factor is 0.9 and the learning rate is 0.1, and let's see what happens.
Okay.
So I think this kind of puts us in a good position if we want to try to understand how these updates happen for a stealth quiz.
No, you tricked me.
Yeah. So here we are in Quizland. Here's what we need to do. We need to say how the weights change as we do these various updates. So in particular, let's start the weights off at 1. So all the weights are 1. So the value that we assign to state 1 is going to be, 3, right? And these will all be 3, actually, except for this one, which will be 8. And I said that the value for state 7 had to be much bigger than the others. Let's say that 8 is much bigger than 3. It's not generally that much bigger.
Well, it depends. Certainly 8-year-olds are much bigger than 3-year-olds.
All right, so assumption validated. So now what we'd like to do is say, what happens to weight 0 when we make any of these transitions on the right here, except for 7,707. Let's look at this particular transition from state 1 to state 7 with a reward of 0.
Okay.
So the weight is currently 1. What is the weight after this update takes place?
For just the 107?
Yeah, that's right. After the update just for the transition from state 1 to state 7 with a reward of 0.
All right. So let's see if the students can do it first. Students, go.
Okay, so what's the answer?
I don't know the answer, but I know how to compute the answer, I think.
That's just as good.
I agree. You just substitute all the values that you have for that equation right there and see what happens.
Okay.
Let's do that. So let's see. Alpha is 0.1 times the reward, which is 0, plus 0.9 times the value, which of where we're headed up, which is 7, which was 8.
State 7, which has a value of 8, right?
Right. Minus the value of the state that we came from, which was 3, times the derivative, the value function with respect to that weight, which is as we recall from earlier, is just the weight, which was 1.
Good.
Right. So that would be 0.42.
Wow, can you really do that? That's impressive.
Yeah, 9 times 8 is 72 minus 3, so that's 42 times 0.1. Yeah.
Nice. All right, so yeah, 0.42. Very good. That means after that first update, weight 0 is actually going to get bigger. Maybe not, not a lot bigger, but a little bigger.
By exactly the 100th of the answer to life, the universe, and everything.
Oh, nice. Little Hitchhiker's Guide reference. Good. And that's what happens to weight 0. What happens to weight 1 after this particular transition from 1 to 7?
I don't know. I guess I'd have to stick everything in again.
No, you wouldn't. It's actually it's very simple because the derivative of the value function with respect to that other weight 2, is just the feature value of that associated with that weight. It used to be 1, but now it's 2. It's just multiplying everything here that we have here by 2.
Oh, that's true. Very good. 0.84.
So weight 0 is going to go up. Weight 1 is going to go up. What's going to happen after we do these other transitions? 2 to 7, 3 to 7, 4 to 7, 5 to 7, 6 to 7.
The very same thing. A very similar thing.
Yeah, ish, right? Because the weight 0 is going to be a little bit bigger than it was, right? It's going to get bumped up each of these times. But essentially everything is growing, and the weight 0 in particular is growing a lot, right? Because it's actually getting updated 6 times, and each of those times is by like 0.42-ish.
Plus a little bit more.
Right, plus a little bit more because it's actually accruing weight gain. Oh, I feel bad for it. I can relate to that. So that's what happens to the weights. They go up and up and up. So that's up to that's these first 6 updates. The updates of states 1 through 6 to state 7. What happens when we go from state 7 to state 7? Let's look at that.
Yeah, we could do that. But I hope happens is things start going down because otherwise things are going to keep going up, like housing prices.
Right, which seems problematic.
Mm-hmm.
Yes, and then you have a bubble, and then, the machine learning economy collapses.
No. Okay. Let's see what happens.
All right, so based on what we just talked through, weight 0 is going to keep going up after each of these updates. And in fact, if you just, plunk it through, it's not particularly complicated, that after these first 6 updates at this point, weight 0 is about 10.4. And now we're going to finally do this last update of state 7 going back to itself. So let's work through that update here.
Okay. Well, that should be pretty easy. We just do what we did before. We substitute in everything.
Okay.
So let's see. Alpha is still 0.1.
Yep.
R is still 0.
Yep.
Gamma is still 0.9.
Yep.
The value of 7 is 7 times 10.4 plus, I guess, still 1.
Yep.
Which is a 2.8, so 73.8.
I'll take that.
Minus the value of S, where we just came from, which we just said was 73.8.
Yeah. So we're making a transition from state 7 back to state 7. And so the value of S and the value of S prime are the same.
Right. And then it's just the feature.
Which is
7.
7.
And that's equal to some kind of math thing. That's not that hard. It's minus 0.738 times 7.
Negative 5.166.
If you say so.
All right, so that's kind of good news, right? Because this weight 0, which had been getting, pumped up and up and up and up, is going to come back down a bit. And in fact, now...
False. That's not good because W0 went up a lot more than you're about to take it back down.
Well, sure. Yeah, so weight 0, after all these updates have happened, the weight is 5.234. It started off at 1, recall, and now has actually blown up quite substantially.
Mm-hmm.
So this last update does help, but it doesn't help enough. Is that what you're getting at?
Yeah, and in fact, that's going to keep happening because it didn't matter that we started at 1 in particular. There's nothing magical about 1. The point is It's going to keep getting bigger and bigger and bigger and bigger, and that's actually true for W1, W2, W3, W4, W5, W6, and W7.
Right, so if we finish this sequence of updates and we go and do it again, this weight 0 is going to get pumped up even more. Weights 1 through 6 are also going to get pumped up. Weight 7 is going down, but not enough to make up for the rest of everybody. So so this is bad, right? So we just keep doing these updates over and over again, and we'd want them to converge. We'd want them to kind of get to the right numbers, and instead we're just spiraling out of control.
So they're going to converge to infinity.
I think that's kind of the definition of not converging. Well, it's one kind of not converging, right? It's diverging.
Well, that's depressing.
Yeah, so even in this what would otherwise be very well-behaved example, doing what is clearly the right thing in terms of doing these weight updates actually is not the right thing. So, so bad things happen.
So I think I can convince myself just by staring at it that if we happen to set all the weights to start off as 0, they won't ever move. And the right thing will happen.
Should we check that?
Sure. Let's give it a quick check.
Bang, it's a quiz.
Wow, that was also quick, Michael.
Again, the magic of video editing. So what we want to know is that after all these updates, what happens to weights 0 through 7? They start off at 0. What are they after all these updates?
Okay, let's find out.
Let's find out.
Go.
Let's figure it out.
Okay, well, we should figure it out by doing the same thing that we did before, which is substitute everything. But I think we can do that pretty easily. So let's see. Alpha is 0.1. So that's 0.1 times... let's see, 0, because that's the reward, plus 0.9 times 0.
Woo!
Because all the rewards are 0, minus 0. So that's going to be some number times 0 times some other number, so it's going to be 0.
Right.
So W0 is going to be 0 after the
first update.
First one. But if you recall from last time, we just knew that W1 was just going to be twice as big, and 2 times 0 is 0.
Still, yep.
So that means that after the first update, they'll both be 0, which means by induction or something, that'll also be true for states 2 through 6.
Good. All right, so after we've done the first 6, everything's still 0.
Right.
What about the 7th one?
It just has to be the same, right? So, so 0.1 times 0 plus 0 minus 0, so it's still 0. And W7 would be, well, the same thing. It's still 0. It's all zeros.
Yeah. So we can repeat this update, this whole round robin sequence of updates over and over and over again. And what we're going to do is go from all zeros to all zeros to all zeros to all zeros. So we're stuck at the right answer.
Right. So if we did that an infinite number of times, it'd be infinity times 0. So you're telling me infinity times 0 is 0.
Sometimes. I think it's undefined. But in this particular case, it would actually be 0.
Excellent. So if we start out at least with all zeros, we won't leave the wrong answer, at least in a case where all the weights are 0.
In this case, yeah. And I think that's actually going to be true as long as all the transitions are deterministic. So for this case, it holds, but I think it holds in general if the things are deterministic, because we're going to get the same kind of issue happening here, which is the next state and the state are going to have their correct values. This temporal difference is going to be 0, and then it doesn't matter, and nothing else matters. The temporal differences are just going to keep being 0.
Oh, so that would be true even if we had our other infinite number of weights, right? Remember we said that we could, there's an infinite number of ways to get the right value function, everything to be 0. Because the value function will be 0 everywhere, that means that nothing will ever get updated. So if we have exactly everything set up so that all the values start out being 0, then nothing will ever change.
Ah.
So the exact answer is sticky, if deterministic.
That's just what I would say.
But wait, so that happens to be good in this case.
Yeah.
But I think it's the case that if we have any set of weights where the value function everywhere is 0, you can never escape, even if it's the wrong answer.
No.
No?
No. It's true. It's sticky if the TD error is 0, not if the value function is 0.
Right.
So in particular, in this MDP, the reward is always 0.
Right. You're right. So let me amend my statement. It's the case that if the value functions all are at any given time all equal to 0, then the only way you're going to escape is if your reward is not equal to 0.
Yeah. And if the reward is equal to 0, then being at the value function at 0 is actually a solution to the development equation.
Because there's no error.
So there's no error.
Okay, good.
Right. So this is why the exact answer is sticky. This depends on it being deterministic, though. So if it is the case that, for example, some of the transitions we observe are probabilistic, right? So the next state is chosen from among other possible next states. Then one of these updates can actually move us away from the right answer.
Right.
We'd hope that on average it would move, the different updates would actually move us away from the right answer in ways that all canceled out. And I think that's true. But yeah, the details are iffy, right? So it really depends very much on exactly how the learning rate is set and other issues like that. Yeah. So if it's not deterministic, then we can wander away from the right answer, even if we've gotten it. And then as far as this example is concerned, it seems like we could potentially wander very, very far away.
Or we could wander towards the right answer if we're extremely lucky, instead of having things diverge and explode. I guess the lesson here is that if you're doing this generalization where everything kind of depends upon everything else because you're having these shared weights in your value function, then even in a simple linear case, you could not always converge. You can diverge. Bad things can happen. It's just not guaranteed, which is sad because usually we stick with linear functions so that things are easier.
Right. So at the end of the day, we can create examples where it truly does not converge. So we have no way of assuring ourselves that it will converge unless we deviate from some properties of this particular example. And so what we're going to look at next is actually a value function approximation scheme that is well behaved, that is actually going to do the right thing and converge.
Oh, nice. By the way, can I just say that from a pedantic English point of view, I really appreciate the last sentence you wrote because, cannot is supposed to be one word. But if you were one word here, you would be saying this thing could not converge. But what you're saying is that it can be the case that it not converge, and that space matters.
Right. That is pedantic.
Yes. Thank you, Michael. Thank you so much.
All right. So we're going to talk about a particular kind of function approximator that we refer to as an averager and the whole class of averager function approximators.
Okay.
So this is a kind of function approximator that was actually, or at least in this context, introduced by Jeff Gordon. And when he did it, there was this sort of collective head slapping that happened over the entire community of reinforcement learning researchers because it was just so there. It was so beautiful, and nobody saw it except for him. And so it really was at that time the age of Gordon.
Oh, that's fantastic.
So moving on. So we're going to introduce this averagers concept in the context of a simple example. So imagine that what we're trying to do is represent a function over the line, right? So over this one-dimensional space. So it's going to be some kind of curve. And the parameters that we're going to get to set are the actual value of that function at some particular points. So at x1, at x2, and at x3, we can, move these up and down, these points. And what we'd like is that we define a function approximator so that once we've defined these points, the rest of them will get kind of filled in a natural way, let's say.
Mm-hmm.
And for this story to make sense, they're going to have to somehow be related to averaging.
Sure.
How can we define the value of points in between here, between x1 and x2? Say we want to get the value of some point, just plain old x, as a function of the value at x1 and the value of x2. Yeah. So what would be a natural way to do that? I don't know. You can say more than one if you can think of it.
Sure. There are lots of ways of doing it, but I guess the simplest one would be just to take a weighted average based on distance.
Yes. Which is why, these things are called averagers. So what we're going to do is we're going to say, okay, the value of x, I don't know what it is, but we're always going to make sure it's, I don't know, so 0.8 times the value of x1, which is a parameter, plus 0.2 times the value at x2, which is another one of our parameters.
And that's because of the relative distance between x1 and x2.
Yeah, so it turns out it doesn't matter, but that is a very natural thing to do, to kind of do a linear interpolation. And so what that means is once you nail down where x1, x2, and x3 are, the way that it generalizes, the way that it fills in the rest of the function is like, little line segments.
Mm-hmm.
There's a bunch of other things you could do, and they're all okay as long as what we do is any point that we want to define, we define it as a convex combination of the anchor points. So the anchor points are the ones that we get to set as free parameters, and the value at any other state needs to be expressible as a convex combination of the anchor points. So this doesn't really tell us what should we do for like beyond x3 for things that are out here in the state space.
Well, that's funny. That's just what I was going to ask you. What do we do for extrapolation instead of interpolation?
Yeah, so this is very interpolative. Is that a word?
It is now.
Interpolative. It's sort of interpolation related.
Mm-hmm.
So the constraint that we've got for it to be an averager, it needs to be that the value of any point is the convex combination of a set of anchor points. So we get to define how things extrapolate, but it has to be the case that, for example, for some point, I don't know, x prime out here, its value needs to be defined in terms of these black points, in terms of these other anchor points whose values are going to get to be set. So one natural thing would be to say, okay, we're out to the right of x1. Let's just set anything out here to be the value of x3.
Sure.
So we don't really extrapolate so much as just like flatten it out on the two ends, so we don't get too kind of crazy up or down from where we were. But there's other things that we could do as well. You could also say that if you're far enough away from the points, then it's going to be the average, the just straight up average of these guys.
Mm-hmm.
And as you get closer, it's going to be more influenced by the near ones. By virtue of the fact that it's a convex combination, what does that tell us about the value out here?
Well, it has to be in between the highest and lowest value, that's for sure.
Exactly. That's right. So we're extrapolating, but we're not really extrapolating outside of the data that we've got.
Okay.
And this is going to be a really important property of these averagers to make sure that they're going to be well behaved. All right. So that makes sense so far?
Yeah.
Do I have a good definition of an averager?
I think you do.
So here's a general way of writing these averagers. So what we need is there's a set of states, and we're going to need to define the value at those states. And there's a second set of states, the what I was calling the anchor points here, the basis set.
Mm-hmm. I love basis sets.
To define the value of some state S, we need to know what the convex combination of the basis values we're going to take. So we need to have specified, what the basis set is. It's going to be part of our function approximator is going to get to pick the value at those basis points, and we have to predefine the averaging weight, the convex combination weight between any given state that we want to do an approximation and any given basis point, any anchor point that we want to adopt some of its value for. So these are the parameters that the function approximator gets to alter. These are all predefined things that define how the value of other states are going to be defined in terms of these parameters. So it looks a lot like the linear case, right? Except it's not.
Well, and in particular, aren't you missing something? I mean, I was going to say it looks just like the linear case, but there's nothing in there that forces it to be a convex combination, the way you've written it.
Oh, right. So that goes without saying, but I should probably say it.
Yeah.
These particular weights that we're defining need to make it so that the value of any state is a convex combination of these parameters. So I wrote that in math too. So for all states and basis points or anchor points, the weight between them is non-negative, and they sum up to 1.
Okay.
This lets us express things like these kind of linear interpolation that we mentioned before. And in fact, even these kinds of smooth or maybe even kernelized representations work as well, as long as at any point where you need to make a prediction, there is a set of these weights W that define how we're going to define the value at that point in terms of the value of the set of anchor points.
Sounds good to me.
So harkening back to when we talked about supervised learning in that other class, can you think of any supervised learning algorithms that you can actually express as an averager?
Probably.
Okay, then I think you need to fill that in.
Okay, fine. Well, maybe I'll get lucky and the students will do it for me. Go.
All right, what do you were they able to help you?
No, unfortunately, because I'm doing this stupid linear time. I could just start naming all of them, and then you can tell me which one is right. Well, I could just say that the answer to every single other question we ever asked was K and N.
K nearest neighbors. I'm glad you got that answer, and that was a really good answer to give. I think it might have been a guess, though, and so we should at least convince ourselves that this is a reasonable thing.
Well, let's see. How does K and N work? You find the things that are closest to you, and you let them vote. And if it's a number, or even if it's not, you end up basically taking an average.
So if we know where the anchor points are, which the K, defined points are, and we want to know what happens at some other point, all we have to do is say, okay, well, it's the average of the K nearest neighbors. In other words, it's 1 over K. I think I'm overloading K.
Okay.
That we have a whole bunch of points at where the value is defined, but to figure out for some other point, some point that we want to extrapolate to or interpolate to, we take the K nearest neighbors, like K is 3 here, and we give whatever the values are at those points a weight of a third. And so that's a convex combination of anchor points.
Right.
K and N is totally an averager.
And even the extensions to it, where you take averages based upon distance and such, it's still going to be a convex combination.
Yes, that's exactly right, because they are in fact exactly averaging values together. And in fact, lots of kernel versions of this have that same property. So yeah, K and N and friends.
It really is the answer to everything.
So all right, so there are natural function approximators that have this form. There's other new things that we could define, and all we're constrained by, if we're an averager, is that the value at a point whose value we don't know needs to be representable as a fixed convex combination of some values that we do know. Okay?
Okay.
It sounds like a reasonable thing. It sounds like a fairly general thing, and not a particularly weird and scary thing, but it's just what you can do with it is just brilliant.
Show me the brilliance.
Let's think about what these things imply. So the value of a state, well, under the Bellman equation is this, and nothing scary here, right? This is all stuff that you know.
Yeah.
So now the next thing we're going to do is we're going to say, well, the value of the state that we end up in, since we're in averager land, we can write that as the sum over all the anchor points of how related this state S prime is, or what the weight is between S prime and that basis point, and then whatever value we set for the basis point.
Sure.
All right, so here it is in the context of the whole Bellman equation. So this is cool too, right? I just changed the order of summation and kind of regrouped a little bit. So now we've got max over actions, the reward of that action for the state that we started in. Now we're summing instead of over all next states, we're summing over just the basis points.
Sure.
We're multiplying some quantity times the value of the basis point. What can we say about this value here if we write it, let's say, like this? So we can write this as some function t of the state, the action, and the basis point. And the sum over next states is kind of already built in here, right?
Yes.
I gave this a name. I called it t prime, because I wanted you to see a connection between this and transition functions. So how is this like a transition function?
Well, it says, if you're in a state, you take an action. What basis functions will you go to next?
Right, which you don't. I mean, in the actual MDP, you don't go to the basis functions. But the point is that this acts like a transition function in that it's non-negative, right? And when you sum up over all SBs, over all the anchor points, it sums up to 1.
Right.
Why does it sum up to 1? Because this is a convex combination and this is a convex combination. And so when we combine them, we get a convex combination. We could do the algebra for that, but I don't think we need to. And so it acts just like a transition function. So we can actually fold the function approximator itself into the transitions. And all we get at the end of it is an MDP. So why does it actually do the right thing? Because MDPs have a well-defined unique value function, and that you can find it using things like Q-learning and value iteration.
That's beautiful.
Isn't it though? So what we do is we end up with something that is actually a reasonable function approximator. It's taking the value of some state S prime and writing it as a combination of other states. And then we turn it into, over a series of steps, into a new Markov decision process over a smaller set of states, specifically over just the basis states. And at the end of the day, we know that this is going to be well behaved. We know that it's going to approximate things. Well, we don't know that it's going to approximate things reasonably, but at least without blowing up in a convergent sort of way, because we know a lot of stuff about MDPs.
That's kind of insane.
It's very clever.
No, it's very, very clever. So if I were going to, make too fine of a point on it, what would I end up with a kind of interpretation here? I'm like saying the MDP you're moving over is sort of from basis states to basis states.
Yeah, I think that's a good question. So it's as if we're going from a state to some next state, which is S prime, and then from there we're making an additional mini transition to the basis states, the SBs, and the weights on these probabilities are the combination weights, are the convex combination weights. Convex combination weights look a lot like probabilities.
Right, they do.
So it's as if each time we make a transition to a next state S prime, we make an additional little transition to each of the basis states, and from there we continue. And so we can actually solve out what the value function is over everything by just solving the MDP over the basis states.
Right.
And then we can extrapolate that or interpolate that to anything that we want.
I love it. That makes some sense because the basis states sort of represent a set of states. So really what you're talking about is you're averaging over the set of states that kind of get aliased through the basis function. I think that's beautiful.
Yeah, exactly so. So yeah, we fold our function approximator into the MDP itself.
Done.
Poof. Very cool. So the good news is here's a value function approximator that is very well behaved. The bad news is it's hard to do some things with it because value functions aren't always very well represented as averager type things. There's often kind of weird cliffs and so forth in the value function that are not well captured by just smoothing everything out. But still, this is a really nice idea.
Beautiful.
I think that just about covers it as an introduction to generalization. So I think maybe it's a good time to reflect on what we've learned.
I'm willing to do that, especially if it means I don't have to do another quiz.
Okay, well, but no, I'm not going to do another quiz. But I am going to ask you what we learned.
Okay, I think I can remember some of that. So I think the big thing we learned is that there is both a need for and a way to do generalization.
In reinforcement learning, yeah.
And the need part comes from the fact that for a lot of problems we care about, there are zillions and zillions of states.
You could be our generation's Carl Sagan.
Yes, zillions and zillions of states. And that's a problem because, of course, we'll visit states that we've never seen before, and the chances of us seeing every state an infinite number of times and all that other stuff that the theory requires is just kind of unreasonable. Or at least slow. So it'd be nice to overcome that.
Good. Okay. And methods for?
You talked about a few methods, but I think at the end of the day, it really boiled down to let's just take all that stuff we learned in supervised learning and apply it.
Cool. But we did talk about some specific ones. Do you remember any particular supervised learning methods that we looked at in the context of generalization and reinforcement learning?
Sure. We looked at linear function approximation, which makes sense because, linear is nice and well behaved, or at least we hoped it was. And it does seem like the simplest, most straightforward thing to do based on what we know. But I think it's worth mentioning that we were function approximating something in particular, right? So we were deciding to do the value functions and to try to learn those. That's how we were doing our generalization.
Right. That's a good point. We actually looked at different functions that we might approximate, value functions, policies, and models. And we focused primarily on value functions. Models, right. There's interesting things to say about that. But it's not nearly as well studied or as well understood. The value function case, we just focused on representing like the V function or the Q function. And that could be done in a number of ways. Mm-hmm. And we looked at kind of a general gradient form where we turned the Bellman equation itself into a kind of an error measure. And then we looked specifically at linear value function approximation, how you could, if you have a set of features, you can map them to values using a linear function and how we might learn that linear function.
Right. And that's pretty much what we spent almost all. I don't think we did hardly anything with policy function approximation.
Nope.
And that's okay. And one of the reasons it's okay is because you were able to talk about lots of successes that people have had doing function approximation with value functions.
Yeah, and there's some successes on doing function approximation with policies as well. In fact, a lot of the coolest stuff in robotics in the reinforcement learning setting has happened where there's an actual gradient taken with respect to a representation of the policy. It's not exactly clear why it seems to be the more effective way to use feedback in the robotic setting, but it it's worth noting at least that this is doing policy gradient methods do seem to work well in the robotic setting.
That's a good point, but it doesn't really matter. It's not like robotics is the future or anything.
Robotics is totally the future.
We'll see. We'll have this conversation in 2050 and see what we think.
In 2015, it is 2015.
No, 2050.
Oh, 2050. Oh, phew. I'm like, oh my gosh, it's the future, and I wasn't even paying attention.
Well, that's okay. I, for one, welcome our new robotic overlords.
Oh, good.
In the meantime, we had all these successes, and you named a few, right? The one I remember the most was TD Gammon, but there were others, which if I went back and looked at what we recorded, I'm sure I could find out what they were. Or maybe you'll just remember.
Well, I mentioned several, but Atari is one that actually came up relatively recently, and hopefully will actually change the way that people think about this whole topic of generalization. But we'll see. I mean, it's still too new to know.
Oh, very good, Prince. Okay, so now those successes, of course, were followed by the downer of problems and sort of problem cases where things that seem like they would obviously work do not obviously and easily work, even in the case of linear function approximation.
Yes, that's exactly right. The good news is in the last few years, there's a new set of methods that are based on TD and a gradient, but it's a different kind of gradient that actually uses the function approximator as part of the error metric that's being resolved, and that these can actually, these provably converge. For the case of linear in particular, the paper that talks about GTD2 actually shows what happens when you apply this particular problem case, the Baird counterexample that we looked at, and you can actually correctly learn it if you use this other update rule instead of kind of the classic Bellman residual minimization kind of thing. What they showed in some of the recent work is that you run into problems if you try to minimize the loss function that we talked about, which is trying to minimize the kind of TD error directly. And instead, you actually get something that's much more well-behaved if you incorporate the function approximation itself into the loss function. So take advantage of the fact that we know that we're changing parameters that are ultimately going to influence a linear representation of the function, and that through that linear representation of the function, that's where we're going to actually measure the loss. And so the projection with respect to the function approximator ends up showing up in the loss function, and that makes things happier.
Oh, nice. Well done. So we had successes, we had problems, and then we have successes again. That's pretty good.
Yeah, and one other thing to note on the successes side is that the current, we didn't talk about this so much, but the go-to algorithm these days is called fitted Q iteration, which is a way of mixing function approximation and Q-value learning together that, again, it has the same kinds of problems. It need not work. It need not converge. It can behave really badly. But this is something that a lot of people have gotten to work decently. So if you're trying to solve these kinds of problems, this is the go-to. GTD is not quite there yet. It's more of theoretical interest, but the hope is that these will actually come more together in the future. And there's one other topic that we spent time on that I think is worth mentioning, which is the notion of averagers.
Yes.
And the cool thing about an averager was not only were things well behaved, you got convergence with a function approximator, but it actually could be viewed as a kind of MDP itself. The function approximator could be viewed as a kind of MDP itself, which lets us get all kinds of nice properties like that there's a unique value function that it needs to converge to. One thing we didn't talk about that's also really related to this topic is in the averager case, we had a set of anchor points. Remember that?
Yes, I do.
As the number of anchor points increases, the error in the value function approximation that you get actually goes down. And so you can actually converge over time on not only an answer, but actually the right answer, the right value function in the limit.
Right, because this was just K and N, right? Or was a lot like K and N. And that would be true for K and N as well.
Yes.
Right? If you had an infinite number of points, for example, you could actually represent the function.
So in our optional reading, we'll actually put a link to the first paper that really goes through that argument and shows that, in fact, as the amount of data increases, things like averagers, kernel methods, converge to the optimal value function, the true value function.
That's way cool. So is that everything we learned, including stuff we didn't learn?
I think that's everything we learned and a bunch of things that we didn't learn. And then I probably should also just say LSPI and just leave it at that.
I think that's right. We have to leave them to go learn something on their own. Otherwise, what would the point be?
Yes. Least squares policy iteration, which is a kind of linear function approximation where policy improvement is actually incorporated into the system itself, and it has some super nice properties, and people have gotten it to do good things. The tricky thing is always the feature set, getting the right features so that linear function approximation does an okay job.
Well, that's always true, isn't it?
Exactly.
I mean, it's if we could always have the right features, then the problem becomes easy.
So that's a lot to learn.
Yeah, and to have learned. What are we going to do next time, Michael?
Here, I'll give you a hint. I'm hiding the slide. We're going to talk about partially observable models.
Okay, that makes sense. That means like lots of opportunities for puns.
All right, we'll see you there then. Wouldn't want to miss that.
See, it has already begun. All right, well, bye, Michael.
See you, Charles.